Okay, today we are going to look at geometric sequences, and this will be our last lesson before spring break, and then after spring break we'll pick up with what are called geometric series. But sequences you should have seen in Algebra 1, so most of this should be review, but we'll go through each of these and how do we write the formula for them, as well as what they are. So a sequence is usually a list of numbers, so there's two sequences shown up here. Okay, and they usually have some sort of pattern to them. So if we look at these two sequences, we want to identify the pattern. So the first one, 3, 5, 7, 9, this is adding 2 from one term to the next. That pen did not work. Okay, so that would be our pattern. So if we wanted to find the next term, we would do 11 plus 2, that would give me 13, and so on. Okay, in our second sequence, 3, 6, 12, 24. Okay, if we try to think about an addition, this would be adding 3 from 3 to 6, but then it would be adding 6 from 6 to 12. So that's not the pattern. Okay, the other way to think about patterns is multiplication. So 3 times 2 gives me 6, 6 times 2 gives me 12, 12 times 2 is 24, and so on. Okay, so instead of adding here, the pattern is using multiplication. So sequence A, or the first sequence, has a constant difference. Okay, the difference between the two terms is always 2. Okay, and that's called an arithmetic sequence. And you may remember that from Algebra 1. And that basically is a linear type of sequence because you're adding or subtracting the same amount each time. Sequence B has a ratio, okay, which is what we're multiplying by, of 2, and that's called a geometric sequence. And those are going to be the ones we focus on, because if we're multiplying by the same value each time, that's going to be an exponential type of pattern. So that's kind of why it fits into this unit here. Okay, so if you're multiplying by something, that's called your ratio. So geometric sequences have a common ratio, which means to get from one term to the next, you multiply by a common ratio. Now, sometimes they'll be real easy to see, sometimes it may not. So if you don't see the common ratio, you can always go backwards and divide. So like if I did 6 divided by 3, that gives me 2. That tells you what your common ratio is. Or 12 divided by 6. Okay, that also gives you 2, so that's your common ratio. Okay, so there are two types of formulas we'll look at. The first one is called the closed form formula or explicit formula, and this is basically like the function. What can I plug in and get something out? The other one is called the recursive formula, and all this does is basically tell you what the pattern is. Okay, so you can describe what's happening in the sequence. So this one's not as useful, it just kind of shows the pattern. Okay, so our closed form formula looks like this, and we've got all different types of variables going on. So the first one is a sub n. It's kind of like your y equals, and that n represents the term. So this is talking about the nth term. Okay, but when we're writing our function, we just write a n equals just like we write y equals. Okay, so a sub 1, just like this was the nth term, that's going to represent the first term. And we'll actually put a number in for that value, and don't put, a sub whatever. It's going to be an actual number. Okay, the r represents your common ratio, or what you're multiplying by. Okay, and then m represents a term number. That's kind of like your x. What can I plug in for? Okay, so this will be, it'll look similar to an exponential function. It's just your exponent is a little bit different. Instead of being just raised to the x, it's raised to the n minus 1. And we'll talk about why that is in a little bit. But we're going to find the closed form formula for that sequence we had up at the top. So 3, 6, 12, 24. Okay, so an, we don't plug anything in for that. That's like your y equals. So a1, we need to find our first term. So that's basically just the first number in your sequence. So that's the 3. Okay, times R. So R is your common ratio. So this was multiplying by 2. So my common ratio is 2. Okay, and then we're going to leave our exponent as n minus 1. That's just finding the function. You're not plugging any specific value in. It's just this is our function to go along with this sequence. Okay, if we wanted to find a specific term, it would say like find A4 or find the 4th term. That's when you would go through and you would plug in a number. So we do 3 times 2 raised to the 4 minus 1. And so that's going to be 3 times 2 raised to the 3rd power. And that would give us 24. Okay, so that means our 4th term was 24, which we already had that up here because this is term 1, 2, 3, 4. So our 4th term is 24. Okay, so this one's more useful. That's what you'll use if they want you to find a specific term. Okay, now the recursive formula looks a little bit weird, especially as you write it out. You're like, I don't understand why I'm writing this. So I'll try to talk you through it, but it's just almost like a description. How do I describe what's going on? So AN, that's the same thing as it was over there. That's your nth term. Okay, that's like your y equals. So A sub n minus 1, that's going to be the previous term. Okay, and I'll talk about why in a second. And then R is still your common ratio. So basically, the only way this is useful is if you're trying to find like a next term. So if you know the 3rd term, how can I find the 4th term? So I'll write the formula and then I'll kind of explain what it looks like if you want to find a term. So if we want to find the recursive formula for this same sequence, we do AN equals, you actually leave the AN minus 1 because that's going to depend on what term you're looking to find. The only thing you plug a number in for is your R. So we know our common ratio is 2, so we would put times 2. Okay, so basically what this means is to get from one term to the next, we multiply by 2. Okay, so if I wanted to know the 4th term, okay, I would have to know A sub 4 minus 1, and then I would have to multiply that by 2. Okay, so this means I need to know the 3rd term. So the 3rd term in my sequence is 12, and then I would multiply that by 2, and that would give me 24. Okay, so this is only useful almost if you're in the beginning of the sequence. If you wanted to know the 30th term, you would have to know the 29th term to even get there. So pretty much what you're going to be asked to do is just write out that formula just so you can see what the pattern is. Okay, it just tells you how to get from one term to the next. Okay, so those are our 2 different types of formulas. So we'll do one quick example on that. And then we're going to compare these to exponential functions on the other side. All right, so number 1 here, we're going to do all of these things. So it'll look pretty similar, but just putting it all in one problem. So the first one says, determine if the following sequence is geometric. So does it have a multiplication pattern? Okay, does it have a common ratio where it's multiplying by the same thing each time? So I know 3 times 4 gives me 12, 12 times 4 gives me 48, and 48 times 4 is 192. So this would be yes, because I'm multiplying by the same amount each time. And that common ratio would be what I'm multiplying by, which is the 4. Okay? And again, if you couldn't tell, you have to go backwards and divide. Do 12 divided by 3, that's 4. 48 divided by 12, that's 4, and so on. Okay, so our explicit formula, we're going to use that formula up there. So AN equals, that's like Y equals. So A1 is your first term in the sequence, which is 3, times my common ratio, which we just said was 4. That's what we're multiplying by. And then your exponent is always n minus 1. Okay, now remember, you cannot multiply those together and put 12 to the n minus 1 because it's only the 4 that's being raised to the n minus 1. Okay, and then our recursive formula is AN equals, I'll pull that up a little bit. Okay, A sub n minus 1, We don't change that. We're just plugging in the ratio. So times 4. Okay, and again, this just is the pattern to get from one term to the next. We multiply by 4. Okay, and now if it asks you to find a specific term, so it says find the 8th term, and they could ask that by saying find A8. That means the same thing. You want to use your explicit or your closed formula to find that. So that's where we're going to plug in a value for Rn. Okay, so we do A8 equals 3 times 4 raised to the 8 minus 1, or you could go ahead and put to the 7th power. And these will get large because they're exponential. So 3 times 4 raised to the 7th gives me 49,152. Okay, and if it's small enough, you could always just keep listing out the numbers, but you want to be able to use the formula as well. Okay, so those are our 2 formulas. You'll have those on your notes, but if you need to go, or on your worksheet, but if you need to go back and look at this, that's kind of where our examples look like. Okay, so the back side, we're going to look at comparing when do we use exponential functions versus when do we use a geometric sequence, because they do seem pretty similar. So this first part, we're just going to decide which one we would use, and then we'll do one example at the bottom. Okay, so this paragraph is super important because it tells you the difference between them. So the explicit formula for a geometric sequence is very similar to the formula for an exponential function. So if you remember, exponential functions look like a times b raised to the x. Okay, however, this is the difference. Exponential functions start with x equals 0. Okay, because remember you had to start at your y-intercept. Okay, so that a value represented your y-intercept, or where x is 0. Where geometric sequences start with x equals 1. Okay, so we're not starting at the 0 term, we're starting at the first term. So the best way to look at this is, are you starting at 0, okay, or are you starting at 1? So in word problems, you kind of have to look for, is it an initial value, or is it the first day or the first hour? And that'll help you tell the difference between those. So we're just going to go through number 2 and look at, okay, would they be best represented by an exponential function or a geometric sequence? And you can use both, okay, they both work, but there's a best answer for each one. So letter A says you invest $2,000 in a bank account initially, okay, which grows at 1.5% yearly. So if you started it, no time has passed. So that would be where your time is 0 or where your x is 0. So this would be best with an exponential function. Okay. Letter B, on the first day of track, so you see that keyword there, you had to run 2 100-yard sprints. Every day for the next week, you would double the amount of 100-yard sprints you had to run. Okay, so we're starting on the first day, so that means you're starting where x is 1. So this one would be best with the geometric sequence, since you're not starting on day 0, you're starting on day 1. Okay, so kind of similar with the next two. See, on your first birthday, your grandma gave you $200 to put in a bank account. The bank account grew by 5% each year. How much money would be in the account when you were 10 years old? So we are starting at your first birthday, okay, not when you were born. So this would be a geometric sequence. Okay, and then the last one, the scientist had 5 bacteria cells in a dish. The bacteria doubled each minute. So he's starting with 5 before any time had passed, and then after each minute it doubles. So that means this one's going to be an exponential function because you're starting where time is 0. Okay, so that's really the difference as to when is a sequence better than an exponential function. Okay, so we're going to do one example where we actually do both so you can see the difference there, and then you guys can work on your practice. So a Starbucks gift card is being sent via, that should be sent, not sent, via Facebook. The gift card is spreading to people in the following pattern. So notice this starts on day 1, not on day 0. So day 1, there's 2 people. Day 2, there's 6. Day 3, there's 18. So does this represent an exponential or linear function? Okay, so this is going to be exponential because we are multiplying by 3, okay, not adding or subtracting. Okay, so B says write the exponential function modeling the number of people that have the Starbucks gift card. So if I want to write the function, that's when I'm doing the A times B raised to the X. Okay, so I actually need to go back to day 0 to get that initial value. Okay, so if going this way, I'm multiplying by 3. To go backwards, I'm going to have to divide by 3. So 2 divided by 3 is not a whole number. Okay, that's going to give me 2/3. Now, it doesn't really make sense in context, but it's just going to give us what the function would look like. Okay, so my A value is 2/3. B is what we're multiplying by, so it's multiplying by 3, okay, raised to the X. Okay, so now we're going to do the sequence. So use your closed form formula to find the formula for the geometric sequence. Now, this one's probably going to make more sense because we are starting on day 1, okay? So A n equals, so A sub 1, that's my first term, so my first day, there's 2 people. Okay. It's multiplying by 3 and then raised to the n minus 1. Okay, so this n minus 1 basically allows it to shift from where x equals 0 over to where x equals 1. So kind of think about your transformations. Okay, this shifts your graph over 1 whole unit. So it still is going to match up, but it just changes that starting point. Okay, so if you compare the formula from question B and question C, okay, they still have the same ratio, but the differences are going to be your starting value and your exponent are different. Okay, but if we were to type these into Desmos or your graphing calculator, you would see that these actually are the same exact graph. They're just written in 2 different ways. So they still will work. It just depends on which one is the best way to model depending on the scenario. Okay, so on your practice worksheet, you'll do that on Showbie, but you'll be using your 2 formulas here for most of it. And then there's 1 or 2 word problems for you to work on. So let me know if you have any questions, and hope you guys have a good day.